Okay, so I'm going to talk to you tonight about stars that actually are in multiple systems where they're orbiting around each other. And through various processes, the stars can actually merge and become one star when there were two stars before. It's actually something I do for my own research. And a little bit what I'm going to be talking to you about is stuff that I'm actually doing. I just came from a conference in Aspen this summer. They have these programs called the Aspen Center for Physics programs. And the program I was part of is called Interacting Binaries and the Transients They Cause. So this is the case of interacting in the extreme because they're actually not only just interacting, they're actually merging. I hope it will be not too technical for you, but there's going to be a little bit of science here, and anybody gets lost, we're all good friends. Just raise your hand and say, slow down. Please explain what you're talking about. But first, let me just tell you a little bit about myself. I'm a professor of astrophysics since 1987. I'm in my final year, sabbatical year, it's called, where I can actually travel around, visit colleagues. I'm going to visit my colleagues in Australia over the winter, and some colleagues in Europe this fall. But the main thing is that for the last 15 years or so, I've been teaching a course called Fundamentals of Astrophysics. And when I was asked to teach this course, it was a new course, so I had the freedom to design the course. And I found that it was very hard to find good textbooks because the level is not just introductory astronomy for people who have no math. It was intended for students that have a background in engineering, other sciences, or even astronomy itself. Sophomores say that I had a year of freshman calculus. And I found the textbooks really weren't very good. So I ended up writing notes for the students. And over the years, the notes kind of developed to a textbook that then is published now by Cambridge University Press. And you can get you can get this through Amazon, for example, if you just Google my name. Now, it does assume you know calculus, but I think it's actually it's written in a kind of conversational style. So you don't have to necessarily follow all the calculus to get a lot out of this book. The other thing is that I have 3 grandchildren. I was mentioning this at the beginning. And the 2 top books were written for my 2 granddaughters. One of them is a granddaughter who lives in Colorado. Her mother asked me, she had heard a radio show on PBS about a guy who wrote some books called Quantum Physics for Babies and General Relativity for Babies. Some of you may know these books. And it was inspired to me to write a book about my work, which is about massive stars, very big stars. And it's a poem, and it's about 10, 12 pages long. Then my second granddaughter was born. My daughter asked me to write something for her. And I've been teaching in the class about the scales of the universe, about how different sizes of the universe, each time you go to a bigger size by a factor of 10, you can sort of characterize all the things in the universe. And so this is the number 26 jelly beans. A little girl asks her grandpa, what's the biggest thing? And he says, well, it's hard to explain it, but I can show you with these magic jelly beans. Each jelly bean will make you 10 times bigger. And after 26 jelly beans, this little girl is as big as the universe, the known universe. So you might find that fun, and you can, if you want, you can copy these links down. You can find them on the web, and I do have some hard copies. I have 1 hard copy with me. And then for my courses I've written a couple other poems about the Earth and the sun. But that's just a way of just the advertisement, you know, like a Netflix these days. If you want the cheap version, or not Netflix, I guess it's various streaming things, you know, you have to listen to an ad at the beginning. That's kind of what we're doing here. Okay, so the main thing I wanted to talk about is our sun is a single star, which is orbited by 9 planets, if you will. I still think Pluto should be a planet. I voted against it being demoted. But it turns out that most stars are not single stars. They often are in 2 stars that are orbiting around each other, circling around each other. Sometimes there's even 3 or more stars. And particularly for very massive stars, for big stars that I study, this is quite common. And when they orbit around each other, they pull on each other, and they don't orbit around one, like everything in the solar system orbits around the sun. You know, we see that on the screen. Because the sun is so much more massive, it doesn't really wobble at all due to the orbits of the planets, very little. But most other ones, they orbit about the center of mass, the mass between them. If the more mass of the planet, the more it kind of the closer it is to the center of mass. And if it's very massive, then it basically orbits around that star. But it turns out that when planets or even any two bodies are orbiting around each other, like say the moon going around the Earth, they don't just orbit around each other, they distort each other because the gravity is a little bit stronger on the side of the face facing the other body. And so gravity pulls that material a bit more. That's how we get tides on the Earth. And so the moon causes tides on the Earth, and the Earth causes tides on the moon. But if you now were to make them stars and start moving them close together, the effective surfaces of where matter would like to go, called equipotential surfaces, will actually become distorted. So in this case, for example, these two stars are equal to each other, their mass, and so they orbit about the common center of mass. But it turns out if the stars were to get bigger, so that their size starts to become comparable to the separation, then they can actually fill this little surface here and spill matter over onto the other star. So binary stars that are orbiting around each other in space and other systems often interact with each other. They spill mass from one star to the other. Because when stars age, kind of like people, they get bigger. Like I've certainly experienced that. And when they finally get so big, the rate at which they get bigger, it depends on how massive they are. So the more, if you have two stars in a binary system, and one of them is more massive, it will expand up and it will spill matter onto the other star. So here's another diagram sort of showing this. And it's a little bit busy, but let's just take a deep breath and think about this a little bit. These are two objects that are orbiting around each other. These are the equipotential surfaces projected on this plane. There's kind of like another rendition of the equipotential, the gravitational. Again, this is potential from gravity and centrifugal forces of the stars orbiting around each other. Now, one of the things I want you to notice is that there are these little things called L1, L2, L3, L4, L5. Those are places called the Lagrange points. They are places where the potential has a kind of it's like the top of a hill or the bottom of a hill. They're like either wells or little, like the top of a hill. So does anybody know, for the case of the Earth going around the sun, there's a very famous satellite that is placed particularly at one of these points. Does anybody know which point and what satellite I'm talking about? Yep.
Oh, what?
At James Webb. And which one is it at?
2.
L2. So this is the Earth. Then L2 is on the other side where the sun is. And it happens to be a kind of like a place of minimum potential. Now, it turns out to be one that's unstable. It's like a surface that is like that. And so you can put it there and it wants to stay, but it slowly drifts away. So it has to use its fuel every once in a while to stay there. But that's where James Webb is, looking back out into space away from the sun and being in the L2 point. Okay, but when you come to stars, these points, the most important point, well, there's actually a bunch of satellites that sit at L1 that are there to look at the sun. And they orbit around the Earth, they orbit around the sun with the Earth, but they can always look at the sun because they're on the sun side of the Earth, on the day side. And so those are two popular places. And then these places are actually L4 and L5, places where asteroids tend to accumulate because those are really, those like little valleys. And so people, like for Jupiter, for example, this is where Jupiter has these similar points like that. And that's where a bunch of asteroids collect. And that's how we get, well, there's actually a mission to go study, these are called the Trojan asteroids. All right, let's get back to binaries. The key point is that many times stars are not the same mass when they're orbiting. One star is more massive. And as I said, that more massive star, as it bloats up, during its natural course of aging, will spill matter onto the other star. And the net result of this is that the mass ratio gets changed. And so you end up with something like this, little peanut stars, stars that are called contact binaries. Now, if you go back and you look at this L2 point for these stars, this is the place where mass can easily leak away from the stellar system. And that loss of mass sort of takes away energy and angular momentum, spinning motion, and it makes the two stars come closer and closer together. And so what do you think eventually happens? They merge. Now, do we actually see this happening? Well, this can take billions and millions of years. So we have to be pretty lucky to see any digit binary system. But there are several 100 billion stars in our Milky Way galaxy. And if you just watch enough of them, you might have an opportunity to see one actually going through a merger. Or you can look at the star and see the results of it having recently merged. Okay, are we all together? So what I'm going to show you now is a computer simulation, three-dimensional hydrodynamic, or using also magnetic fields are in there. The whole 9 yards. Nowadays with modern computers, we can actually do this kind of remarkably. And this is done by a collaborator of mine, Fabian Schneider. He's at Heidelberg University. And this simulation was done by one of his colleagues there. So I'm going to show you a movie of the simulation. Let's see if I can get it to work. So there's the stars going around each other. This is looking face on, and this is looking edge on. The top is the density, looking at the cut of the density. And the bottom is magnetic fields that get generated by the shearing gas. And eventually you end up with a very rapidly rotating single star. Okay, any questions at this point? All right, so does this actually happen? Do we see evidence of it? Well, for a long time, I've been very interested in this part of the sky in the Southern Hemisphere. It's one of the most famous places. This is a picture, composite picture done by a colleague of mine, Nathan Smith. This is called the Carina Nebula. It's in the Southern Hemisphere. You can't see it from here. You have to go to the south of the equator. But there's a bunch of really funny things going on here. And there's a lot of mass, a lot of gas and stuff that's in the process of collapsing into stars. All this lit up is just from stars lighting up the nebula. It's really quite beautiful. This is taken by the Hubble Space Telescope. You can actually search, and the web has, I didn't download it, but there's a picture, a similar picture taken with the web. The web actually looks at longer wavelength light, infrared light. Anyway, you can see all kinds of stuff going on here, but I want you to focus on this guy right here. This is called Eta Carina. It's thought to be one of the most massive stars in our galaxy. It's about 2,300 parsecs away. Anybody know what a parsec is? No? It's 3.26 light years. Light years is the distance that light travels 1 year. Okay, so this is about 9,000 light years away. When we look at Eta Carina, we're seeing what it was like 9,000 years ago. Okay? Now, what's really interesting about Eta Carina, it's not just a star, it has this really beautiful nebula. Let me show another picture of it, where we estimate the amount of mass that was ejected, that was lost from this star, was more than 10 times the mass of the sun. The star itself is estimated to be about 100, maybe 130 times the mass of our sun. But it has these two lobes of material and a bunch of stuff surrounding it, and then this kind of equatorial skirt, right? How did it do that? Because the star is still there. This is not the result massive stars, when they finally run out of fuel, will collapse and make something called a supernova, where they blast material away. And usually all that's left behind is a very tiny thing like a neutron star or a black hole. This thing still has a star in the middle, lighting up all this nebula. And so what happened? Well, it turns out, historically, if you look back to the records, Eta Carinae got really bright, got to about observed magnitude of, you can see it with the naked eye. It was actually not as bright as the brightest star in the sky, but when it got its peak brightness, it was bright. And this is only known from people who lived in the Southern Hemisphere in the 19th century. In the 1840s, it got as bright as, say, a bright star that we see today for a few weeks. And so this, the date here is in 1843 is the peak or so. And then it got really much dimmer. And today it's starting to rise up again. Now, unfortunately, you don't have a modern telescope to be able to look at Eta Carinae when it had this eruption. I don't have time to talk about it, but it turns out that the light from Eta Carinae actually bounces off the surrounding nebula, and we get what's called light echoes. And you can't study the spectrum of those. But that's almost a whole nother talk. So I'm going to leave that aside for now. I'll come back to it in a little bit. And the key thing I want you to know is that Eta Carinae got really bright, and it ejected more than 10 times the mass of the sun in the 1840s. Now, it turns out today, Eta Carinae is a binary. It's got another star orbiting it every 5.5 years. And Eta Carinae is so bright, it's more than 5 million times brighter than our sun. And this other star, we don't see it directly, but we see the evidence for it in something else. We see evidence for it when we look at the star in X-rays. Every 5.5 years, the X-rays from this system go up and they drop, and then they come back. 5.5 years, they do it all over again. Why is that? Well, it's because Eta Carinae in its binary system, both of these stars are very bright. They're so bright that they push away matter from them in something we call a stellar wind. I happen to be somebody who studied stellar winds for many years, since I've come to Delaware. And so, of course, I was very interested in this. And I had a student who basically modeled the collision of the two stellar winds from the two putative stars. His name is Chris Russell. He's a support scientist at Delaware right now. I think he'll get a permanent job eventually. But he has PhD thesis with me modeling the X-rays coming from this by accounting for their stellar winds. So I'll just show you briefly a movie that he generated. There's the secondary star. There's Eta Carinae. The secondary star's wind plows into the primary, and it makes all these X-rays. There's a model that Chris Russell did for his PhD thesis under me. And by calibrating how hard the X-rays are, we kind of figure out what this ghost star must be. We can't see it directly, but we can see its imprint by how it impacts Eta Carinae every 5.5 years. So, how did Eta Carinae eject so much mass? What happened? What caused it to eject, say, 20% of its mass in the 1840s? Well, this is a movie that shows Eta Carinae as it's viewed by the Hubble Space Telescope from 1995, shortly after the Hubble was launched, until 2008. I don't have a movie that comes up to today. But what do you notice? Eta Carinae is getting bigger. It's expanding. We can actually see this in front of our eyes. We can see it getting bigger. So we know the speed at which the material is being ejected from that expansion. And we know that when you go back and track the expansion, it goes back to the 1840s, right when Eta Carina had this huge bright eruption. So they must be related to each other, right? What happened in 1840s? Well, we think it was a merger, that two stars actually merged. But wait a minute, Eta Carina is a binary today. So if two stars merged in 1840, what was it before that? It was three stars. It was a triple system. Now, one of the things, when I was a little kid, there was a Twilight Zone episode about the sun being kicked out of its orbit and the Earth being kicked out of its orbit and falling into the sun. Why don't we have to worry? Anybody? Because the Earth's orbit's very, very stable. Two bodies going around each other just keep doing it because they have this amount of angular momentum they have to maintain, and they have this amount of orbital energy that binds them together. And those things don't change during the course of an orbit. You can solve that analytically on a laptop. You can find out what the orbit will be millions of years from now. It's very, very stable. What happens if you put a third body? You get something called the three-body problem. The three-body problem, just among people, is very unstable, right? Two bodies can last forever for 50 years. I've been married to my wife 41 years now. But three bodies will do chaotic things. We all know that. And so here is an illustration. What happens if you have three stars orbiting around each other? Sometimes two of the stars go together real closely, and the other two, they get swapped. I mean, I hate to push the analogy too far, but you know, right? So the point is that if Eta Carina was a merger, that at one point it was three stars, and that was very unstable. And so what happened as the two stars were going around each other to the inner stars, they finally got to the point where they got old enough that the more massive star bloated up. It spilled matter onto the other star, but the net result of that was to separate the stars more. And now the other star, which was pretty far away, now that the two stars are separated more, now that other star comes in and says, whoa, wait a second, I'll swap with you. And so originally, the two stars that we think merged, one of them was in the middle, one of them was an outlier. Then the bigger star got big enough that it spilled matter over to the other star, right? That star got more massive, brighter, stronger, but it got separated more, and then their star came in and took its place. And then the other star got kicked out. That's the binary, that's the star that we don't see today. And the two other stars merged. Okay, now, that's amazing. Here's the scenario put together by my colleague from Oxford. He's actually Japanese. He lives in Australia now. I'm going to go visit him in January. So you have this stable triple system. That's the mass of the three stars. Is there a pointer somewhere? Okay, that's all right. On the tray? Okay, great, thanks. Thank you. Do it on the screen, that way the people at home will be able to see it. That's all right, I'll use the screen because that way people at home will see it. Okay, so this is the original thing. The two stars, 60, 40, 50. Then what happens is one star gets bloated up and causes the orbit to widen. And then it gets these close encounters, which then cause these ejecta, and we see these ejecta going off in all kinds of random directions in that outer envelope. I didn't give the details of that. And then there's chaotic swaps, And the star that gained mass is back now over here. Oh, sorry, I'm sorry, that lost mass is back over here. And then these two stars merge and they make the system we see today. Now, we wrote a paper about this. We tried to get it published in Science, couldn't get it past the referees. So we published it in the Standard Journal in 2021. And Rio Harai, he was Japanese, but he grew up in England, so he speaks the Queen's English. It's pretty unusual to have a person who's Japanese to be speaking English. So he's a great guy. All right, so that is Eta Carina. Any questions about this? Anybody have any questions? Have I lost you guys? No, you're pretty much following along. That's good.
I've got a question.
Sure.
Considering you're talking massive stars, right?
Right.
So with our solar system, I mean, we've got a lot of bodies orbiting each other. How come we're not seeing these erratic orbits?
Well, because they're far enough separated that they don't, in the current day solar system, they don't interact with each other very much. Jupiter is the biggest guy. Jupiter does perturb asteroids and comets that are flying around. And every once in a while, it causes one of these comets to come into the inner solar system, and it hits the Earth. That's why we're here today, because the dinosaurs got wiped out by one of those. So Jupiter is like the little mixer here that's kind of causing chaotic things to happen. In the early solar system, when the solar system was first forming, they all had to kind of clear out the orbit. What happened to the Earth in the early solar system? Another body that was in the same orbit smashed into it, and it made the moon. This is our current understanding of where the moon came from. There's even a belief that the two outer planets, Uranus and Neptune, swap position. And during that time, send lots of bodies into the inner solar system. This is what we call the late heavy bombardment. Most of the craters, the big seas that you see on the moon, came from that epoch. And during that time, that's probably where most of the water we have on Earth came from. Yeah. So the moon, one of the things about the great results of Apollo, when they brought back samples from the moon, they found that the fundamental isotopic abundance, that means certain elements have different isotopes, that how much mass is in the nucleus compared to the number of protons. The pattern of the moon exactly matched the Earth. They had to come from the same stuff. And that led people to realize that what happened in the very early solar system, when the solar system was just getting organized, that there was another body, probably something the size of Mars, that impacted the Earth and kicked out and made the moon. The moon is actually very unusual in that it's only about a quarter the size of the Earth. Most of the other moons that are going around the other giant planets are tiny compared to their big central thing. The moon is really amazing. And if we didn't have the moon, who knows? We probably wouldn't be here. But my point is that the early solar system was very chaotic. But then once everything cleared out, it became very, very regular and ordinary. And that was very lucky for us because it gave time enough for things to be nice and stable, except for a few comets hitting the Earth every once in a while and killed off the dinosaurs. And that's why we have the system we have today. Yeah.
Is that kind of peanutty shape, stable, or is that going to?
The peanut shape that starts.
Will that become a ball?
Oh, you mean the ejecta? The ejecta that we see?
What's
No, the ejecta's flying away. That ain't coming back. But the peanut that was there earlier, that can last for billions of years, depending on the details. But when it finally collapses, it's very sudden. It's dynamic. It's kind of like a slow burner. It then eventually ignites. Good question. Anybody else? Yeah.
There are two scenarios, right? One scenario where the material spills off to the other star.
Yeah, that's early
There's a
on.
second scenario where it emerges. Like, when does what happen? Like, when does it spill and when does it emerge?
So the two stars they're in a triple system, but they're pretty stable because they're orbiting close by, and the other guy's out an outlier. So he just sits there and it just sits there passively. But then, as the two stars during normal stellar evolution, stars tend to get big. Our sun will eventually become a red giant. it'll blow it up to 100 times its current size. It'll fill half the sky. It'll burn up the earth at that point. That's not for 5 billion years, so you don't have to worry about it. I once gave a talk about that at my kids' elementary school, and I got all these notes. I can't believe the sun's going to burn up the earth someday. So anyway, but in any other system where you have two stars going around it, the more massive one does this earlier because it's burning fuel much more rapidly. Massive stars are much more luminous than our sun. A star that's, say, 100 times the mass of our sun is 1,000,000 times as luminous. So that means it uses up its fuel really fast. And then when it finally does, that's when it expands into a giant. And when it does that, it spills its mass over onto the other star. And that's inevitable. If you have two close binary systems, you're going to have mass. That's called Roche-Lobe overflow. Roche is the potential. And so that happens first, but when that happens, that separates the two stars. And then the other star is no longer just an outlier. It's close enough to kind of cause some chaos. And that's what's happening in the phase.
Why
Well, that's a little bit complicated. You got to know a little bit about orbital dynamics to understand that. If you want, we could talk afterwards. I don't want to go through a lesson in orbital mechanics right now. But I will tell you that it has mostly due to the changing the ratio of the mass of the star. You have to conserve things like angular momentum and so forth. And it turns out the only way you can do that is to separate the stars further. Yeah.
Supernova.
Yeah, we're going to get to that.
I was curious about this one.
This guy is going to go supernova someday. Hasn't done it yet. Not in our lifetime. It'll take well, it could happen tomorrow. We don't know. But we will find out that there are stars in binary systems, close binary systems, that go supernova, both of them. And when they do that, they leave behind pretty crazy things, neutron stars and black holes. I'm going to talk about that a little bit. That's kind of the end of the talk. Well, actually, we're getting pretty close to there. Now, first thing I wanted to say is that, well, this happened in the 1840s. We don't really, all we have to do is look at sort of like, we have to be like forensic scientists, we have to kind of look at the remnant of what we see and piece together what's happening. But the universe is a really big place. And now that we have robotic telescopes that are looking at millions of stars all the time, we can see these events going off in other places. And there's a particular kind of event called a luminous red nova. Now, a nova, standard nova, is when mass fills over onto a collapsed dead solar type star called the white dwarf, and it gets onto that surface and it triggers nuclear fusion, and the star erupts. And we see something called a nova where the star gets bright for a while. Then there are, of course, there's supernovae, where the star actually collapses and dies. And we see a really much more luminous thing. That's why they're called supernova. Luminous red novae are in between. They're in a kind of a gap between the novae and the supernovae. And they're called red because they are very, very red. And so what are they? We think they are merging stars. And so I took this from a wiki page, and basically they think to be merging stars. So do we have those going on today? Well, there's this interest in astronomy called the time domain, looking at not just the stars as they exist today, but what happens if you look at enough stars and they're going through some crazy phase, if you look at enough of them, you're going to find those. So there is this observatory that was designed to look for transient events. It was what's called OGLE, Observatory for Gravitational Lens Events. Now, this gets a little bit off the beaten track, but we think that there are a lot of very, very dim things floating around the universe. And every once in a while, they should go in front of a star. And Einstein said that a gravitational source in front of a star should bend its light. And when that happens, you get this pulse of of variable light. So Ogle was built to find those events and to find how many of these dead objects are floating around in space. But accidentally, they observed this guy. And this guy is not from a gravitational lens event, not from a looking for low mass things. This is an actual merger. And when you looked at it, it had this characteristic spectrum of these luminous red novae. So we think this was the smoking gun of a merger. Now, this star was only about 1.5 times the mass of the star. It merged with something that was about 0.2 times the mass of the star. This is much lower mass object, much lower luminosity. But we see these red novae of all kinds of different luminosity. So we begin to realize that there's this whole class of things which are probably mergers. Here's another one. This had this eruption. Look at this in 2002. So in other words, the important point here is that this is happening today or in our modern telescope era. So we have much better data. And there's another one, it's from 2002, the 838 Montserratus, which is the name of the constellation it's in. I think this was a merger. And here's the kind of smoking gun. This star is, when we looked at with the Hubble Space Telescope, it got this beautiful expanding light coming from it that evolved over a period of just a couple of years. How did that happen? If you actually calculated the speed at which something would have to move away, it would be faster than this, or comparable to the speed of light. So this isn't actually an explosion. This is a flash bulb going off at some time, and then it scatters off all of the material, but it takes longer for light to scatter off something that is not directly coming towards us and then come towards us. So these are light echoes. These are echoes of the exploding source of light. So I could show you a nice little movie. This is what the 838 Montserratus looked like in before this went off, before this event, before 2002. And now this is Hubble pictures of it every couple of years. And you can see it's repeating. You can see this light echo goes off. And then when we look at the spectrum of this thing, it's luminous red nova. And so there's lots of evidence now that this was a merger. A little bit more massive than the other one, but still not as massive as Eta Carina. Okay, so the point about this is that we don't have to just go back to the historical record. We can actually look out today with our modern telescopes and find examples of luminous red novae. And so one of the things I left Aspen with my colleagues is, gee, wouldn't it be cool if we could find analogs to Eta Carina going off today, maybe in other part of the galaxy or in a nearby galaxy, looking for the luminous red novae that are very luminous because they were more massive mergers. And that's what I'm going to be going to Australia to work on with my colleague, Rio, and other collaborators. All right, so now this is where we get to the question that was asked. When you have these two stars and they haven't merged yet, they're still orbiting each other. But now one of the stars gets to the point where it runs out of its fuel in the core, and it'll explode. And exploding massive stars, anything that's greater than 8 times the mass of the sun, will leave behind something called a neutron star, or if it's 30 times the mass of the sun, a wind-up black hole. So our sun, when it finally dies, will just become something called a white dwarf. But these other stars, more massive stars, they will become neutron stars or black holes. And if this happens before the two stars merge, then one of them pops off. And if they're tightly enough bound, they stay bound. Then the other one pops off. And now you have two collapsed objects, either neutron star, black hole, or black hole, neutron star. Now, it would be cool if we could see one of these merger, if a merger finally occurs from a black hole. But what's the problem with that? How are we going to see the mergers of two black holes where the rule is that light can never escape from a black hole. So we can't see it with our eyes, with our telescopes, because it doesn't give off any light. But what it does do is give off waves in gravity. The gravitational force of space, Einstein taught us, was a bending of space-time. When you have, I could give a whole talk about this, but when you have gravity, what it really does is bend space-time. And what light or matter does is try to follow the minimum of, follows around that curvature. Kind of like if you look in a museum, one of those, a science museum, you see a little ball going around on a conical thing. It's going around, it's just following the trajectory in space-time. That's how Einstein explained gravity and explained things like orbits. It's a bending of space-time. A black hole is a bending of space-time where it actually punctures. Think of it as like a trampoline in which you put a bowling ball in it and it stretches. But then if you make the bowling ball heavy enough, it breaks the trampoline. And that's essentially what a black hole is. So now if you have two of these balls going around on the trampoline, what do you think happens to the shape of the trampoline? Does anybody have an idea? It's going to be waves. And so Einstein predicted that these two black holes that are getting closer and closer to each other are sending out waves in space-time. Now, that means you can't see them with a telescope. You need a gravitational wave observatory. Now, the problem with this is that gravity is incredibly weak compared to the forces that make things like light, electromagnetism. It's 25 or something like 20-something orders of magnitude weaker. In other words, the force between two protons pushing apart is 10 to the 23 powers bigger than the gravity that's trying to pull them together. Electromagnetic forces are very, 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 very weak. For example, what's holding you down in your seat right now? Gravity of the Earth. But the molecules of the plastic in your seat is strong enough to keep you from falling to the center of the Earth. This little tiny chair can overcome all of the mass of the Earth, right? So gravity is incredibly weak. And so it turns out to see these gravitational waves, firstly because they're coming from very far away, you need an incredibly sensitive instrument. And that's what this laser interferometric gravitational wave observatory, or LIGO, has achieved. In 2015, Einstein published his theory of gravitational waves. I'm sorry, 1915. Sorry. In 2015, the first gravitational waves from merging black holes was observed, almost exactly a century after Einstein predicted. Einstein himself thought we'd never be able to predict. Because what happens is, as the gravitational wave goes by, there are two lasers that are bouncing off mirrors, this one in this direction, this one in this direction. And it actually is able to detect the difference in the length. The gravity stretches space in one direction and compresses it in another direction. But the deflection, the size of the deflection is 1/1000th of the size of an atomic nucleus, of the size of a proton. 1,000. Think about this. These mirrors are able to detect a change in the size of space by 1 part in 1,000 of the size of an atomic nucleus. That's what. But with 20 years of effort from the time that NSF said, let's do this, they gave them enough money, they kept it stable over 20 years, so they kept refining the instruments to the point where they're able to do this. The way they were able to do this is they have one of these in Louisiana and one of them in Washington State. And by looking at correspondence signal between the two, they can filter out local noise. So that was done in 2015. We now have detected over 100 merging black holes since then. Here's what you see. You see a deflection in the space, little ringing. That comes from the stars getting close, the new black holes getting closer and closer, and they're orbiting faster and faster. And so you see this ringing. And then if you play this on a audio, you hear this little chirp. I should have gotten that, but it goes like that if you play it out in audio. Yeah, what's really amazing is by modeling this, you can actually figure out what the two masses of the black holes that merged. Turns out in this case, it was about a 31, 32 solar mass black hole merging with a 28. Let's say it's 32 and 28. What does that up to? 60. Turns out that the final object was only 57 solar masses. Times the mass of the sun. What happened to the other 3 solar masses? It was converted by Einstein's formula, E equals mc squared, into energy, which is what powered the gravitational wave. During the time, this millisecond, fraction of a millisecond, that this gravitational wave was being generated by the merging of 2 black holes, this object was brighter in energy than all of the stars in all of the galaxies in the observable universe. For that instant, there was more power coming out of this merger than all the stars in the universe. Now that doesn't blow your socks off. I don't know what. Okay, so, but what if it's not 2 black holes? What if it's 2 neutron stars that merge? Well, now they don't have this restriction. Neutron stars are not inside of the event horizon of a black hole. They're very close, but light can come out of them. So in 2017, just before the eclipse that I was telling you some about, 3 days before that eclipse, they observed a gravitational wave event, and they were able to pinpoint it. It turns out that it made, 2 seconds later, there was a pulse of gamma rays from an orbiting telescope. And then they were able to triangulate and figure out where the gravitational wave was. And they pointed telescopes in, and they saw all kinds, they saw basically the signatures of of merging stars. They saw light as well as the gravitational waves. Yeah, you can take spectra of those light. So here's the merger going on. Just like 2 stars getting closer to neutron stars, you get closer. Here's the gravitational wave they're sending off. You get closer and closer and closer. They merge. There's this big eruption of light, which we see with our telescopes, with our ordinary optical telescopes. Also gamma rays, X-rays, and there's the expanding nebula. Now, one of the coolest things about astronomy is that work from the people in the 19th century, people who studied the first spectra from stars, gave us the tools to tell what stars are made of. This is called spectroscopy. Whenever you have stars with a certain element, there'll be a fingerprint on the star's light that tells you what elements are in that star. The sun, we know the composition of the sun. We know it's mostly hydrogen and helium, and then about 1 or 2% carbon, nitrogen, oxygen, iron, all the other elements of the periodic table. They were able to take spectra of this merging kilonova, this merging neutron stars. And what did they find? They found the elements, some of the elements of the periodic table were coming from this merger. We're mostly made of water, which is hydrogen and oxygen. Oxygen has 8 protons and 8 neutrons, right? So most of the elements that we're made of have equal number of protons and neutrons. But when you go further up the periodic table, there's more neutrons than there are protons. It's very hard to make those any other way. You need lots of neutrons. Well, what's a neutron star made of? It's made of neutrons. So in the explosion, it's very easy to make these high neutron elements. Now, we're mostly made of this stuff, carbon, nitrogen. They come from exploding stars. The carbon in your DNA, the iron in your blood, the oxygen we're breathing, these were all made from exploding supernovae stars and spread back out through the galaxy, forming the Earth eventually. But the bling, I don't have it on because it gives me a rash, but my wedding ring or your wedding, the gold, it came from one of these kilonovae billions of years ago. The bling, gold and platinum, all the stuff down here, everything you see in orange, a lot of it comes from merging neutron stars, from kilonovae. And so the lesson here is we are made of star stuff, mostly. But the bling we wear is made of merging neutron stars. Okay, thank you very much.